Direct memory access, or DMA. DMA is an important concept in the domains of computer systems and also embedded systems. We oftentimes deal with a big chunk of data rather than individual bytes or words. And we need to store such data in buffers. And that's what we call buffering, which is to temporarily store data in memory before processing. And data accumulated in peripheral commonly buffered. Let's say you have a networking device, a NIC card, and you receive network data from the wire or from wireless connections. And these packets will be stored on the NIC device and eventually have to be processed by the main processor. So there has to be some data movement. We have to move data from the peripheral device to the main memory for the processor to process. And we could handle this with ISR. We can store and move individual bytes like we did in the previous two examples, process them and maybe store the updated data to a different place. But when you do this, you have to use instructions to do it, and your regular program will have to wait. DMA, direct memory access, is to make that process more efficient. It will separate the movement from the main processor. The main processor will do its own thing doing the main program, whereas the DMA controller will relinquish the control and relinquish the control of the system bus so that the DMA controller can do the movement. Let me show you again using this diagram. We want to show you the activities of both the main processor and the case with DMA controller. But first, this is the memory transfer without DMA. Let me jump to the next slide. So we're using a vector to interrupt. You see that we have the main program is being executed, and we have data that's arriving, and we have an interrupt asserted. We have interrupt acknowledgement. So peripheral will send a interrupt vector number 16, and using that, the microprocessor will find where the ISR is, which is address 16. It'll read data, modify data, and writes the data to address 0001. So now it's different from what we saw before. In this case, what we want to do is to move the data from the peripheral to memory. And memory is addressed in units of bytes. So we have this byte and next byte and so on. So we have thousands, millions of bytes in here. So when the ISR is being executed, the P1 will deassert the interrupt, and then the data transfer will happen. So the microprocessor will copy data from the peripheral to internal register and another copy. Now in this case, we're copying again, but we will move the pointer to the next location. As we already read the first byte, so this is going to be the second byte or word, and then so on. So we do this continuously, and we will do many times until we finish transferring all the data. And after that, the ISR returns, and then we will have the microprocessor executing the main program again. Okay, so what you noticed was when we move the data, we have to use actual instructions, we're going to have the microprocessor, the main microprocessor, to perform the move operation. Here is the case when we have a DMA controller. So immediately you see there are three things come into play. We still have the main processor, and we still have the peripheral device, which is to receive data. And now we have a DMA controller. Instead of reading this diagram, I'll just show you the animation. So first, if you look at this diagram, we still see the microprocessor here. We still have the data memory. We still have the peripheral device. But now we have an actual hardware, which is the DMA controller. The DMA controller is like a separate, smaller processor. It's a hardware chip, and it connects to the microprocessor, and it connects to the peripheral. In itself, it has a few things, this address 001 and this address 8000. In terms of signals, it has request, acknowledge, and here is the DMA request, DMA acknowledgement. And for between DMA controller and the peripheral, we have a request and an acknowledgement. And inside the program, inside the memory, we have the main program. Here, we don't have ISR. Because with DMA, we are not really doing interrupt service routine anymore. And we'll see how we're actually going to do the data movement. So at the very beginning, the microprocessor still executes its main program, and it has already configured its DMA control registers. Now, this step was not shown here, how exactly, but there are ways to talk to the microcontroller like you talk to the peripherals. So the microprocessor will, before everything, will initialize these registers. These registers are related to where we want to copy the data to, and also where the data is coming from. Like this is the destination address, and this is the source address. So P1 receives input data in a register with the address 8000, we saw before. And then P1 asserts request to request servicing by DMA controller. And the DMA controller asserts the acknowledgement. DMA controller asserts the DMA request to request control of the system bus. So this control signal is to tell the microprocessor that I, as a DMA controller, I would like to use your system bus, which is this part. This system bus is, there's just one set of system bus. Everybody is connected to this system bus. Microcontroller, DMA controller, P1, memory. So there got to be some master to perform the control so that we can start doing data transfer. Typically, is the microprocessor does all this controlling to send out addresses and then move data around. What we're trying to do here as the DMA controller, it tries to say, okay, can I use your system bus? The microcontroller can say no, but if it has no other reasons, it will agree. So the next thing you will see is the microcontroller sees this DMA request, which was asserted. It will decide to grant that access. So it will release system bus and assert this DMA ACK signal. So what really this microprocessor does is to put all of its signals on high impedance state so that it essentially isolates itself from the system bus. So as a result, we would have to, depending on what the microprocessor will do in the next time, when it continues the instruction execution, it may go forward if the instruction only use data inside the microprocessor. So let's say move R0, R1, so which means we're going to copy the data from one register to another register and maybe do addition onto registers. If it does all these things without needing accessing any of these other memory location, it can proceed. If the microprocessor needs to access any of these memory locations, it will have to wait, because the microprocessor, once it released the control of the system bus, it should not really access the system bus. So it's possible that the microprocessor will stop. So for the DMA controller, it's good news that it will get the access to the system bus. It will acknowledge to the peripheral, basically telling the peripheral that, hey, you know what? We got access to the system bus, and now we can do all the transfer we need. So it will read data from the peripheral to its internal register and copy that value to the destination location. Now, the eventual result is the same. The new data is going to be copied to this memory location. But you see the major difference is the microcontroller, the microprocessor here, is out of the picture during that data copy process. That's good news, believe it or not. This microprocessor can execute whatever instruction it has. So all these can be executed while this data copying is taking place. And even better news, if we need to copy, instead of 1 byte, if we need to copy 1,000 bytes or 1,000,000 bytes, all this will be done by the DMA controller. So you have a counter here that will say, okay, copy the next 1,000 bytes. So we'll be copying the next 1,000 bytes and filling up these memory locations. And in that case, of course, you need to update these address by incrementing them, but that's a different story. So once the data copying is done, it will deassert the DMA request and also acknowledge the handshake with P1 to say, okay, I'm done with the copying, to tell the P1 that all the data you have been copied, and also to tell the microprocessor that, hey, I'm done using your system bus, and you are free to take it back. And you are free to take the system bus back, which the microprocessor will be happy to do, and then we go back to the normal operation.